Thanks a lot. Thanks a lot for that kind introduction. I am so excited to see so many students, and I'm told that there are parents as well and teachers as well. So, and I also see some of our current students in APU are also present. So you must have heard some of these. So just hold on. Here you will see more. Okay. So what I'll do is the talk is around speed of light. We will see different aspects of speed of light. And if you have any questions, you can stop me at any time. We can have discussions live and then we can proceed ahead. Or if you think you want to ask at the end, that is also fine. Anything is fine. Let me start with the simplest question and then we will slowly increase the complexity of the question. Let's see, before getting into speed of light, let us get some understanding of what typical speeds are, and then we can talk about speed of light. So let us take, for example, a bus, and then we will also compare with sound, and then we will be basically focusing on light. So my first question is, how fast? So just tell me some number, some typical speed of bus.
Sir, okay, for bus, I think in city limits it is 30 to 50 kilometers per hour.
Okay, I'll take 40. Okay, I hope you don't mind.
No problem, sir.
40 kilometer per hour. Good. And then what about sound?
330 meters per second.
It is 332 meters per second.
Okay, let us put it as 330 meters per second. And what is speed of light?
3 into 10 to the power 8 meters per second.
All right. This is great. And now you all would have studied some kinematics or mechanics and things like that, right? So you know that speed is actually a relative quantity. You can't just ask, hey, what is the speed of some galaxy? You have to mention with respect to whom. Without that question, without that extra clause, this question itself is invalid. So when you say speed of bus is 40 kilometer per hour, with respect to whom? With respect to whom is it 40 kilometer per hour?
A person on the road.
To the ground.
No, with respect to ground. That's a reasonable answer.
Anything that is.
So when you say speed of sound is 330 meters per second, what is it with respect to?
Sir, I think the hearers or the like people who produce the sound.
People who produce the sound. So let us say I start running towards you and I speak. Let us say I'm really strong and I run at 100 meters per second. And then if I speak, do you think you will receive sound sound will travel at 430 meters per second?
So no, I still think it will travel at 330 meters.
Sir, this is the same thing with a Doppler effect, right? Like when you hear a supersonic jet, the jet is moving faster, which is why you have to hear the jet. You can slowly see it, the pitch starts changing.
Or an ambulance.
Doppler effect.
Okay. Yeah. So what is Doppler effect? Just remind me, what is Doppler effect?
Something that's approaching towards you, the frequency will be higher. If something's going away from you, the frequency will be lesser.
Frequency,
it's observed with light also. Yeah.
Frequency, right? I'm talking about speed. Does the speed of sound vary with the observer moving?
Sir, the speed is the same. The reason why you get the Doppler effect in the first place is, sir, the speed is the same, but the occurrence of those waves starts changing just by there's a change in frequency. So the speed is constant. Doesn't matter.
So now I guess the relative speed will change.
Relative speed,
because your wavelength has to remain the same. So your velocity and frequency will compensate.
No, the question is velocity is with respect to whom? When you say 330 meters per second, you have to specify with respect to this.
It's with respect to a person standing on the ground, a person who's now moving.
So what
about medium also.
But
Light is
that moving,
the
that non-moving
mechanical wave.
also starts to become relative.
Can one person speak at a time?
Yeah.
So there was some destructive interference. I couldn't get what was actually told.
I said that 330 meters per second also refers to the medium, because light is a mechanical sound is a mechanical wave, and it also depends on the medium of transmission.
So medium makes sense. Medium. In this case, if you say 330, it's I guess it is with respect to air, right? See, ground has nothing to do with sound propagation. Suppose you produce sound, and the sound is propagating, and some magic happens and ground disappears. Sound has nothing to do with it. It will just propagate, right? So this speed has to be with respect to the medium. Okay, that's cool. So now let's get to light. When you say 3 into 10 power 8 meter per second, it is with respect to whom?
It doesn't matter. It's same for everything.
With respect to everything, it will be the same for everything.
I see. So suppose
speed of light changes with the medium.
No, let us. So when you say 3 into 10 power 8 meter per second, what did you have in mind?
Vacuum.
That is in optically rarer mediums.
Okay, so let us stick to vacuum. So when you say 3 into 10 power 8 meter per second in vacuum, it is for those who have not seen some advanced stuff. You just think on your feet, and can you tell me what is it with respect to?
So with light, it starts getting tricky.
Light starts getting what?
It starts becoming difficult to pinpoint with respect to, because it's moving so fast. So
no, the magnitude of the speed is a separate concern.
Okay,
we will come to that.
Fine.
But
okay,
now,
sir,
take a step.
I would say with respect to the source.
With respect to the source.
Yes.
Okay, so let me ask again the same question. I hold a torch. I start running towards you. Let us say I am again very strong and I can run at 1 into 10 power 8 meter per second. I run at that speed and I switch on the torch. So what will be the speed of light?
Speed of light is
Sir, isn't the speed of light absolute value?
Yes, sir. What will happen is that so what will happen is that even if you, like, for example, you have a bike moving at the speed of light with a headlight on, the light will still move at the speed of light, but it will start becoming red shifted. Then you start getting into all the
colors has to do with frequency. I'm not worried about frequency. I'm only interested in.
Yes, but the speed of light will stay the same. Speed of light will stay the same.
So you must have heard this speed of light.
But when refraction happens, doesn't speed of light change?
Yeah.
Because of the medium.
It is.
Okay, sir. Then I would say same thing for sound as it's like the medium then.
Yeah. So let's get to that point that someone made. When you say refraction, you need to have a different medium, right? Change in the medium. So in the vacuum itself, the question is with respect to whom is speed of light so and so?
With respect to a relatively stationary object.
When you say stationary, you have to say with respect to whom is it stationary?
So with respect to the observer.
With respect to the observer. Which observer? Suppose I am here and you are moving. With respect to whom is it 3 into 10 power 8 meter per second? And when you ask this question, the most important thing is you should delete all the friendly environment of Earth, these trees and this atmosphere and all that. Imagine that in this universe, like two of us exist and there is this light propagating. And two of us can be in relative motion. So with respect to whom is it 3 into 10 power 8 meter per second? So this...
Both of us. With respect to both of us.
With respect to both of us.
And I also have to ask one thing. In 10th grade, we learned about how the speed of light changes with the refraction. But I'm not too sure about this, but I don't think we have learned the complete thing. I think speed of light is same in all mediums because it's an electromagnetic wave, and electromagnetic wave do not depend on the medium. So I believe
No, it's not correct. That's not correct actually. just depends on the medium.
Is always an absolute value.
Wait, no. There are multiple things here. When you say electromagnetic waves propagation is independent of medium, that's actually not correct. We will see how actually medium gets into picture, maybe down the when we go down the top. Okay, but to come back, somebody said that look, it doesn't matter who you are, in the sense that it doesn't matter whether what is your speed with respect to anyone. Don't worry about anything else. When you measure speed of light, it turns out to be 3 × 10⁸ meters per second. Full stop. So if for example, let us get back to this case of bus. If there is a bus moving at 40 km/h and you have another vehicle, let's say you have a bike and you are moving at 30 km/h in the same direction, with respect to what will be the speed of bus?
10 km/h.
10 km/h, right? But that doesn't happen with light. If there is a light moving and I measure that, speed of light is 3 × 10⁸ meters per second, and there is someone else who is traveling with respect to me in the same direction as the light, and that person's speed is 2 × 10⁸ meters per second. What is the speed of light with respect to that person? It is not 3 minus 2 × 10⁸ meters per second. It is not 1 × 10⁸ meters per second. It is still 3 × 10⁸ meters per second. Right? That's actually wonderful. Huh? Okay. And how is that? Is a good question. We will come to that. So another way of putting it is, suppose there are two.
I have one more doubt.
Yeah.
So like since velocity and frequency, they both are related.
Yeah, I mean the wavelength also plays a role, right?
Yeah. So different stars and other sources, I mean the illuminating sources, they emit lights of different frequencies. So
Correct.
doesn't their velocity changes?
No, velocity will be the same. The wavelength accordingly changes.
Okay.
C is held constant.
Sir, I got a doubt. So let's say there's a lamp, for example, and then the light hits an object and comes towards you. So before it reaches your eyes, you move back in the speed of light, so you won't be able to see the object. So does that mean relative to you, the speed of light is 0?
No. You will always measure speed of light equal to 3 × 10⁸ meters per second. So I will come to that. I will address all these. So imagine another situation where two buses are moving at 40 km/h in opposite directions. With respect to bus A, what will be the speed of bus B?
80 km.
80 km/h, right? Whereas if there is a light beam moving at 3 × 10⁸ meters per second and someone else is moving at 3 × 10⁸ meters per second, as observed by me, I am observing these two. One is light and another is a person moving at 3 × 10⁸ meters per second. So with respect to this person, what will be the speed of light? It should have been, the naive guess would be 6 × 10⁸ meters per second, but it doesn't happen. It is still 3 × 10⁸ meters per second. So speed of light with respect to anyone, irrespective of the state, is 3 × 10⁸ meters per second. So this is just some, at this level, it's actually info. I'm not proving this. Huh? See, this question actually troubled people for almost a century. Okay, so 19th century was basically going around this question, and it took Einstein to make that bold statement that it doesn't matter what is your state of what is your frame of reference, you'll always observe. So 3 × 10⁸ meters per second. Now somebody asked, hey, how is it possible? Shouldn't the velocity add and get subtracted in the way we know? Isn't that how do you calculate relative velocity? So v1 is the velocity of one observer, and with respect to that observer, if the object is moving at velocity v2, then with respect to me, isn't that object moving at velocity v1 plus v2? Right? That's the usual velocity addition law, right? Vector v1 plus vector.
Basically because nobody can see light.
That is fine, but we can measure speed of light, right? I am observer, I measure speed of light, and with respect to me, someone is moving, and that someone can also measure speed of light. And both of us get the same answer, even though we are moving with respect to each other. That's the point. So the main crux of the matter here is, when you say relative velocities add like this, subtract like this, you have some underlying notion of space and time. That actually is true only for slow enough speeds, and that notion has to kind of get nuanced, kind of get modified according to experiments. So when you are dealing with speeds relative to close to speed of light, so that's the bottom line. But
the faster you go, slower the time, right?
Yeah. So all those things are there. Let me not jump into that because it takes its own path by itself. So for now, let us say that doesn't matter who you are, you will always measure speed of light equal to so and so. Okay. Now actually comes the main question that I want to address within this talk. How do you know? Somebody said, oh, speed of bus is 40. One second. So somebody said speed of bus is 40 km/h. If you are pushed to the wall and somebody holds a gun, hey, tell me how you came to know speed of light or speed of bus. What can you do?
Measure it by distance by time.
Measure it by distance by time. Can you quickly elaborate what you actually meant by that?
We just divide the distance it covered by with the time it took to cover the distance.
Which time?
A distance from one starting point to ending point. We just fix the distance.
So when the bus hits some point, you switch on the clock, and then you note down when the bus hits some other point and switch off the clock. You know the distance, you know the time. Distance by time gives you speed. That's a reasonable experiment, right? So I'll just put a tick mark here, saying it's kind of easy. You can do it. Now, when somebody says, "Hey, speed of sound is 330 meters per second," how can you do that? I can't kind of.
The principle
You
of
can
echo.
go into a place.
Principle of echo. What is
Yeah.
So we can go and we
to a
can
place
echo in
which
one
has
area,
a
and then
lot
you
of
can
echo.
calculate how much time it took to go and then come back. Then divide distance by time, divide again by 2, because going and coming is there. Or we can make the twice the distance from here to that point divided by the time it took.
Okay, that is great. In which case, let me suggest this experiment. You tell me yes or no. So you go and shout. As soon as you shout, you switch on the clock, and when you hear the sound again, you switch off the clock. And if you know the distance, 2 into distance divided by time will give you some number, and you note that down as speed of light. You do it 10 times and take average and all you do. Okay. Now is this good enough? Okay, so let me say that, okay, this is also fine, something that you know. Now let us do the same experiment with light. Do the same experiment with light. We will keep a mirror. We'll switch on the torch. As soon as we switch on the torch, we will start the clock immediately, simultaneously. And as soon as you see the light, you switch off the clock, and then you know the distance, you can know the time, and then you know the speed of light. Shall we tick that as well?
No, because the speed of light is too light moves too fast for us to capture the time in a clock.
Yes, sir. Sir, what I would suggest is using a similar circuit, but we would use a photon detector or a photodetector where it sends out a beep as soon as it hears. Then you can find out the time interval.
Okay, so let me just suggest you are living in 18th century. Now, can you answer the question?
No.
But when was speed of light?
Use photoreceptors.
Sir, I have a doubt. Sir, you told that the speed of light is constant for each and every observer. Then does that mean that the speed of sound is also constant? Because we usually have that notion that speed of sound is 330 meters per second.
It is with respect to the medium. Light doesn't require any medium, unfortunately. And how do you know light?
Sound is mechanical.
But usually we write as the speed of light in the glass is 1 into 10 to the power of 8. Like
that is all in
that.
medium. That is in medium. That's yet another level of complication. But let us talk about vacuum. Within vacuum, when you say speed of light is so and so, you can't point out to something saying that with respect to this, speed of light is so and so.
But sound we can.
Sound we can, yeah. There is no question. I wrote medium, air, and all. I had written no sound. There is no issue.
Okay.
So we can find the frequency and wavelength, and then just figure out the speed.
How do you find out the frequency? What is the typical frequency of visible light? Red light, let's say.
So it's a huge range.
Right.
540 into 540.
Go ahead. Into. I'm interested in that into 10 power. Okay, that also I'll tell you. That number I'm interested in. Will it be what, like 100 hertz, 1000 hertz, 10,000 hertz? What does it look like?
So 10 to the power of minus something, right?
10 power minus something hertz, which means for one cycle to get over, you will have to wait for so many seconds, is it?
There's something into 10 to
540 into 10 to the power of 14 hertz.
10 power 14 and all I heard. Huh? So that's actually something that you can't measure. Huh? I'm not saying you can't measure, but it's not trivial to measure.
Yeah, and 700 into 10 to the power of 14 hertz, the range.
Yeah. So it's huge, something of that order, but it's huge. That's the point I wanted to convey. While in principle it is fine, but in procedure, in practice, it's very hard to chase frequency and then get, hey, this is going to be the method I'm going to adopt. So let us actually wait. So Galileo actually did this experiment. He had his assistant somewhere, and he said, hey, I will open my his way of torch is he had some kind of lamp and then a shutter. Hey, I will open my shutter. That's like switching on the torch. And as soon as you see, his assistant was standing in on another mountain or something like that. Galileo was on one mountain, and then assistant was instructed before itself to open his torch as soon as he sees the light, and Galileo has to observe that light and note down the time difference between what? Between he opening the torch and then he observing his assistant's light. And when he did this, he got distance by time is equal to so and so. It was not a time difference. Time difference was not zero. You may think that it's so fast, it will all happen. It didn't happen. He actually took some time. When he repeated it, he again got back, consistent answers. He got back, hey, look, time difference equal to so and so. Time difference equal to so and so. He got consistent answer. But he did not jump into the conclusion that look, distance by time is equal to so and so, so this is the speed of light. He did something extra to say that, hey, there is something wrong here. Can you guess?
But wouldn't there be a lot of manual error in that experiment?
Yes, the
manual error means what in the case?
The time taken
to remove the shutter is more than the time taken for the light to travel from one mountain to another.
Okay, you all have got it. You all have got it. So it's basically your response time and your assistant's response time that you are noting down, and not the speed of light itself. And now, suppose even in speed of sound, I can always claim that, right? Hey, it's because of some response time you are measuring something, and it's not this tick mark is still questionable, I would say, because I can claim that hey, that is also because of response time, right? How do you actually clarify here?
But sir, if we are using the principle of echo, there won't be another human sending you back that.
That's okay.
Sound,
another human being is just a dummy person. I mean, you could have replaced him with a mirror, right? And light going and hitting a mirror and coming back is same as echo. So my claim is that whatever time difference you measured here is actually because of your response time. It has nothing to do with speed of sound. I have made the claim, so you refute that. Hey, I want others to participate. I see few people are participating. That's great, but others also jump in.
So we can find between the two satellites, no, sir. The photoreceptors in the satellite
I
collector
am a
is.
person sitting in 18th century.
Oh. So, but the photoreceptors were invented in 18th century.
Okay, so I'm sitting in 17th century. Is that okay? I mean that of course that may solve the problem, but that will also
the basic
take away
thing
the
is
fun.
it is not possible for a human to measure such a such a small time difference. Like
That's
the
well and
light.
good. Well and good. You are actually arguing in my defense. Actually, I am claiming that look, this is because of human error. I'm saying that this is response time that you are recording. Even what is this? You remember this medium, this middle column, right? This is actually about sound. I'm saying even for sound, what you are measuring as time difference is basically because of all the human factors.
Sir, but
No, sir, sound we can measure effectively because the time taken for the sound to travel in a medium is basically measurable for humans' eyes. But when I speak about the speed of light,
I'm not convinced. I'm not convinced.
So to get an echo, we need to stand at like some farther distance. Sir, if you keep some object in front of your mouth and you can't do an echo. You have to stand some 17 meters away, no, sir. So, so if you stand at a really, really far away distance, then you have enough time to give away the sound, then for it to come back and then record it, sir. So
okay, all right. So that's viable. So what you are saying is, hey, look, when you say distance by time, when you say, I will just go some, just hold on. I don't know. Yeah, let me go here. So when you say speed equals to distance by time, you shouldn't naively use this formula. You take different readings, you take different distances and different times, which will generate different times, and you will get some data. And then if you are worried about, hey, this is the human error, that y-intercept, ignore it. You just measure the slope. The slope should give you the speed of light. That's a reasonable way to put it. Okay, so that solves it. And now let's come back to the question. Speed of light is still unanswered. How do you know speed of light equal to so and so? You should really have 1 second. You should really have a large distance, right? Can you? Is that
So we can increase the number of mirrors.
But
so the orbit of the Earth,
long distances and mirrors.
Planets.
Long distances and mirrors. So how exactly can you?
So we
what
can.
Is a good answer?
So there's a source of light, and then there are multiple mirrors faced in such a way that the light keeps reflecting off them, and you reach a large distance that way.
That's fantastic in principle, but I'll tell you what is wrong with that in practice. Now, if you get into an optics lab, you will see mirrors are always great. You can kind of control the path of light, but the main problem is it will absorb some light in every reflection. So if you have too many reflections, you will not see the light at the end of the day. And how many reflections do you really want? Let us say you have a big house, some Mysore palace or something, and just calculate how many reflections you need, even with that big space. You need to measure 3 into 10 power 8 meter per second. And if you are really truly in 17th century, you do not even know whether that is or something, or then maybe it's infinite. Who knows? It's infinite probably.
Sir, should we think of this experiment we don't know the speed of light and we're trying to calculate, or we already know it's 3 to 10 to the power of 8 and we're thinking we should calculate?
It doesn't matter. It doesn't matter. No, okay, let us say you know 3 into 10 power 8. You got a dream that it's 3 to 10 power 8 meter per second, but now you can't go and announce it to the world, right? Oh, I got a dream. Let's say you want to prove it.
From what I've heard, the speed of light, this is all I heard a long time ago. That when the speed of light was first measured, it was by using, I don't know, data from planets. That is Jupiter satellites.
Okay.
Which I think is a good enough distance.
Okay. So you're absolutely right. You're absolutely right. Actually, before getting into this, let me propose an experiment. You just evaluate the possibility. You all know sun, right? And sun emits light, and we are very thankful of that.
Yes, sir.
And what is the time taken for light to reach from sun to earth?
8 and a half minutes something. 8.5 minutes.
8 point something minutes. And what is the distance?
Sir, 1 astronomical unit.
Which is
150 million kilometers, I think. I'm not sure.
Yeah, it's 1.5 into 10 power 11 meters. All right. So if you divide 1.5 into 10 power 8 meters by 8 point something minutes, you will see that you will get close to speed of light. And I propose this as an experiment. What would be your response?
Sir, as a person in 18,
So that's,
I don't know how.
sir, actually that is
As a
kind of
person in
weird.
1820, as a wait.
Sir.
But how would you know when?
Sir, I don't
but
know
then you
if
have a
that-
problem. The whole reason you know the speed of light, the whole reason you know the distance from Earth to Sun is because you use speed of light in the first place.
No. I know I can measure Earth sun distance independent of speed of light. I can do it as a geometry problem.
Yeah, I've seen them. Kepler did this, right? He used Venus and he triangulated using
But
trigonometry.
Kepler has no idea about speed of light.
But he found it.
So he did not know that light will take 8
Correct.
minutes to reach the Earth, sir, from Sun. Because we don't know that it's going to take time to reach, sir. Because we are seeing it after 8 minutes. It's not like we see one part of the sun coming and then 8 minutes later another part comes. Whole sun is coming after 8 minutes. We don't see that 8-minute gaps because the light is coming.
That's right. So many others also try to point out the same thing. So distance is not the problem. Distance somehow you can measure.
Sir, but
independent of
how
speed
would
of
you
light.
know when the light starts coming from the sun?
Correct. That's precisely what was pointed out. So although you cannot see when the light actually left the sun, which means you know the time after you know speed of light. It's not the other way around. Okay. So then somebody mentioned Jupiter and all that. So let us get into that. Okay. So this was actually done by a gentleman named Romer. I think there are 2 dots or something like that.
Romer.
Ole
So
Romer.
isn't it Christian Huygens?
I think it's Romer. Yeah. That's what I heard in my history books. You can verify it. No, but I can tell you the method. So this is sun, right? And what is this?
Planet.
Which planet? Earth.
Earth. Okay.
And there is one more planet. Just a second. So this is another planet. It goes and then comes back from here. Okay, I can't. So what is this planet? This is Jupiter. J. I will first ask you a simpler question and then I will get into the point. Okay. See, actually, it's a kind of. It looks very complicated, like because both Earth and Jupiter are moving around Sun. Suppose you imagine that you get into a frame, you stand on Sun, and you are now looking at this, and when Jupiter moves, you also turn towards Jupiter. So you are always facing Jupiter, right? In your frame, can you calculate the can you imagine what Earth is doing?
Sir, it's rotating in the same direction but faster than us.
It's not faster, it's slightly slower. So both are actually moving in the same direction, right?
Sir, that means Jupiter is more squished than Earth.
Jupiter is more
squished because of Earth's rotation is slightly bulging at the equator, right? That means
no wait.
Jupiter's bulge.
In this model, Earth is basically a point object. In this question, what is Earth and all is not important. Earth is, you treat it as a point object, And then I'm suggesting that you stand on sun. Somebody is standing on sun and always facing Jupiter. When Jupiter moves, you turn your head accordingly. So in your frame, Jupiter is stationary. So in your frame, how long will the Earth take to complete one full revolution? Will it be 1 year or slightly less than a year or slightly more than a year?
Sir, it will be 1 year.
Where is
It will be less than a year.
I think this will be more than 1 year.
Okay, we have all three answers.
Sir, because Jupiter rotates and revolves faster than Earth.
Jupiter's rotation is, that's first, by the way, see, there are actually 2 points here. Jupiter's rotation is something that we are not concerned about. Whether Jupiter rotates around itself or not rotating.
So the orbit is larger.
Orbit is larger, but it is not revolving faster than Earth. It's not revolving faster than Earth is faster.
Sir, since the orbit is larger, we see that it moves. We say it moves faster, sir.
It won't
on the
move
sun.
faster. It won't move faster. Farther the planet, it moves slower. Mercury is the fastest planet. Have you heard something about Kepler's laws?
Yes, sir.
Third law?
Yes, sir.
Sir, it's
in
taken by
tell me in 2 seconds. In 1 second, t squared is proportional to
R cube.
R cube. So farther the planet, larger will be the time period. It's kind of, its angular speed will be lower, even its physical speed will be lower. Now if you are always pointing towards Jupiter, then what, see, the poor Earth, it has to not just complete one revolution, it has to move something extra, right? Because you are always chasing Jupiter, you would have turned to by some angle, and Earth has to cover that as well. So Earth, it takes more than a year for Earth to complete one revolution, as observed by you. Who are you now? You are always facing Jupiter, standing on sun. Okay, but this is an easy problem to solve. It's basically, you all told how speed of bus gets added with speed of car and all that, right? V1 plus V2. Similar thing you have to do with angular speeds. And once you know relative angular speed, you can calculate the time period. That's easy problem. So since angular speed is getting lower, omega 1 minus omega 2, since both are traveling the same direction, so angular speed gets subtracted, so time period goes up. Whatever it is, let us say you can do that problem. So in this model, Jupiter is held stationary. Jupiter doesn't move from now. Earth moves slightly slower. We have compensated for that. So now there is a catch here. So Earth is currently here, and you now come back to Earth. Let's say another observer is on Earth. This is a very nice situation, right? On one side you have Sun, and exactly opposite side you have Jupiter. So you call such a situation as opposition. So this point I just call as opposition. And then after not 6 months, but slightly larger than 6 months, Earth will be here. When you are on Earth and you are at such a point, you will see Sun and Jupiter along the same direction. Sun will rise and Jupiter will rise simultaneously. Sunset and Jupiter set will happen simultaneously. So that kind of point is called conjunction. See, conjunction.
So it's like eclipse, but with Jupiter.
That's fine, but eclipse need not always happen, given the fact that these are in different planes.
Okay, sir.
Just like every new moon is not solar eclipse. Just like every full moon is not lunar eclipse. You would have drawn similar diagram, right? But not every full moon is a lunar eclipse.
Sir, but when we draw like this, it's on the same plane, no, sir.
When we are unfortunately draw, I see my tab is a 2-dimensional tab, so I'm using that. Okay, but in reality they are in 2 different planes. That's why it's not necessary that there has to be an eclipse here. Nevertheless, now Jupiter has his or her own friends. Okay, so there are moons moving around Jupiter, and one of those moons is called Io. Oh, this is not good enough. So let's see. This one is actually Io. It's in physical size, it's much smaller than Jupiter, but I'm just drawing it just to highlight it. So this Io is moving around Jupiter, and it takes something like 42 hours, 42 point something hours. It doesn't matter what exactly is the time. It takes around 42 hours for it to complete one full revolution around Jupiter. So do you see that every 42 hours this Io will go behind Jupiter and hide? Here in this case there will be an eclipse because Jupiter is really large. Even though they are not in exactly the same planes, Jupiter is really large, and the distance between Jupiter and Io is not appreciable. They are very close compared to Earth Jupiter distance or Sun Jupiter distance. So in this case, every time Io goes behind Jupiter, there will be an eclipse. So you see that there, in principle, there has to be an eclipse every 42 hours. And Romer actually kept observing Io. He kept track of Io. What he observed was the following. So he noted down, he first made a table. See, I'm basically presenting it in as simple way as possible. Okay. So note down serial number. What is the serial number? This is eclipse serial number. First eclipse, second eclipse, third eclipse, and so on. Let us say for convenience, you start from a position. And then what is this? This is second column is time at which eclipse was observed. You note down sometime, and all you get. And then you note down delta T. What is delta T? Successive time difference, right? Time difference between two successive eclipses. So the entry here is this minus this. Okay. So this is what you should expect as 42 hours. And this should also be 42 hours. This should also be 42 hours, and so on. And to his surprise, this time was not exactly 42 hours. So you create one more column. See, 42 is again a representative number. It is 42 point something. Okay, that doesn't matter now. So this delta T minus 42 hours, you note down. This delta T minus 42 hours, you plot it against serial number. Then you get a nice curve starting from an opposition to another opposition. In between there is a conjunction. This is serial number, and on the y-axis you are plotting delta T minus 42 hours. You get a nice curve. And this is a very systematic error. Okay, this is a systematic deviation. It's not some fluctuation. It's a very systematic thing. And this amplitude is 14 seconds, roughly around 14 seconds. Now let us get into some calculation and all. But before that, can you tell me why is there such a systematic deviation?
So the evolution of the moon is aided by the evolution of the Jupiter around the sun too.
Sorry, I didn't get that.
The Jupiter has to revolve the sun too, sir.
No, in our model we have stopped Jupiter because we are always pointing towards Jupiter, right, as observed from sun. So Jupiter, you can take that it's not moving at all. So Earth, on the other hand, is compensating that by moving slightly slow.
Sir, sorry, sir. Sir, is this data, sir, with respect to person standing on sun or person standing on Earth?
It doesn't matter. Here we are talking about time differences. Both will actually observe the same thing. And when Romer did this, he was certainly not standing on sun. And why do you think such a deviation should actually exist?
Sir, wait, I have one doubt before we go any further. I didn't understand how we got that 42 hours.
You take the average of all this, you get 42 hours. You count from, see, what is the average of this last column? Is in other words, see, this is not exactly a sine function, but this is close to a sine function. What is the area under a sine function for a full cycle?
I have not learned that, sir.
0.
Yeah.
So whatever is on the top, it's the same thing on the bottom, right? So on an average means what? If you average over large number of cycles, or if there are integral number of conjunctions that are covered, then on an average the deviation goes away. Then you take the average, you will get the true 42 hours, whatever.
I still not, sir. Yeah, but you've taken the y-axis as delta t minus 42 hours.
Correct, correct.
Where did you take that 42?
Correct, I know.
Where is that 42 hours from the first?
Yeah, fine. I got that. So you basically take this delta t, when I say delta t, this column, and take the average. This won't be constant numbers. There will be slight variations. There will be slight variations, and then you take.
What is delta t, sir?
Delta t is the time difference between two successive eclipses. Difference between these two will go in here. Difference between these two will go in here.
Okay.
And then you take average of all such entries. You will get the true time period of Io around Jupiter.
Why are we taking Io?
This was Io. This orange thing was Io here.
Yeah, sir.
So is it something to deal with the bending of light?
Bending of light. Where is light bending? When you require bending, you need change in medium, right?
Sir, I think he's talking with respect to yeah, I think it's speaking relative to general relativity, which is not even the case here.
No, it's not even.
I think the 14 seconds.
Sir, light bends near the heavy objects.
Huh?
Light bends near the heavy objects.
Yeah, that's all.
Yeah, but that's all relativity. That's all relativity.
Small effects. It can't produce some 14-second difference and all that. They are really they are there everywhere. Light also bends around.
It is there.
But it's too small to observe.
Yes, sir.
Sir, Earth's atmosphere.
Why did we take? Sir. Wait. Why did we suddenly take Io? We were using Jupiter this whole time. Why did we take Io?
No, wait. So Jupiter was of course there, but then we focused on what is revolving around Io. Io, for every around 42 hours, it went behind the Jupiter and it was not visible. That is what we said as eclipse of Io.
Okay.
And that is what we are monitoring.
Okay.
Huh?
So it takes 42 hours for Io to complete one revolution.
Correct. But when you observe, it's not exactly 42 hours. There is a systematic time difference. 42 hours plus or minus 14 seconds. And there is that systematic variation. And how do you conceptually understand this? And then we can try to do a calculation and find out.
So we're trying to understand why is there that variation?
That's what I'm asking. Why is there a variation?
Sir, can we say that the variation is the difference in the time taken by light to reach Earth from Jupiter and time taken by light to reach Earth from Io?
No. It's always reaching from around Jupiter. Whether it starts from Jupiter and Io, it's not that. It's always the same thing, right? It's the same kind of eclipse that's happening. Okay, so
even the Earth rotates.
Earth rotates around. Earth revolves around Sun.
Yes, sir. With the revolution, the rotations are aided. So we due to the revolution of the rotation of the Earth, we feel that there is a time gap.
Rotation is not a player here. Rotation is of course there, but it's not actually. It doesn't contribute. It's the revolution of Earth around Sun that contributes. See, this is what exactly is happening.
Sir, isn't it because Earth and Jupiter have different orbits and different speeds? So the distance between them does not always stay constant.
Correct. So?
Because the distance is not constant, the time is changing.
Correct.
So because the speed of light is constant.
Perfect.
Okay. So this proves that speed of light is finite.
Correct. This was actually the first experiment which showed that speed of light is even finite and not an infinite number. That was the first achievement of Roman's experiment. So basically this emits the information that eclipse has happened, right? That's way to put it. And this information is moving in all directions. In some seasons, let's say this season, Earth is eager enough to collect that information. It is moving towards Jupiter and collects that information faster. On the other hand, because on other seasons, Earth is kind of moving away. So it takes that extra distance for the information to travel, and that's accounts for larger time.
Okay, sir. Are these paths? Are they circular or are they ellipses?
That difference is not that key here. That difference is that they all matter. That when you get into finer calculations, you need to bring in all those things. But at a conceptual level, at the 0th level of thinking, that doesn't matter, because Earth's eccentricity around Sun is really small. If you approximate it to be a circle, it's a very good approximation.
Okay.
So that is not that's not the big deal. So did you actually understand that when you are moving towards Jupiter or moving away from Jupiter, you are actually advancing the information, or kind of saying that, okay, I can wait for that information, because you are moving towards or away. So if you realize this is actually Doppler effect. Observer is moving towards the source or moving away from the source. And when I say that, it is not the traditional red shift or the blue shift that you would have heard. That is the shift in the frequency of light. Whereas I am talking about the shift in the frequency of occurrence of eclipse.
Okay, the information, the frequency of how much you fast is getting the information.
Correct.
Right.
That information is getting Doppler shifted. Right. And you know, in Doppler shift, the speed of light actually gets into the formula, right? And you can clearly find this out. And since you know what is the ray angular speed, effective angular speed at which Earth is moving, so if you know the time, anyway you know the time difference, right? So if you know the time difference, you know this angle. Once you know this angle, you can complete the triangle. You know this distance, and you know this angle, which means you can calculate this distance. And if you do it for the next occurrence of eclipse, you know the updated distance. And once you have it, you're done.
You can get the difference in distance.
Yeah, you get that extra distance, which means you can account for that extra time, and that extra distance by extra time gives you speed of light.
Sir, how did they know the angle in those days?
So you know actually speed of Earth around Sun, right? I mean, you know the angular speed of Sun around Earth. So do you know, for example, what is 1 year? How much is 1
revolution around the Sun?
What is it?
That's one full revolution around the Sun.
And how much time does it take?
365 days, 365.5 quarter days.
And how do you know that?
Because we count the days.
Okay, I am ready to count the days. Tell me, when should I start and when should I end?
I think
from solstice
by seasons.
Solstice to solstice.
Huh?
You calculate from solstice to solstice. Winter or summer.
Solstice. That's what you're saying?
Yes.
Or equinox to equinox.
There are stuff involved. What you are saying is not wrong. But there are simpler methods to calculate speed of light. I mean the duration of year. So once you know duration of year, you know the angular speed of Earth. Once you know the angular speed of Earth and you know the time, you can calculate the angle. Is that a good enough thing to say?
Yes.
Okay. So now I will tell you a kind of a terrestrial experiment. This is all. To do this experiment, if you want to reproduce this experiment, it will take years together, right? And then you'll have to work day and night and all that. So I can tell you an experiment that I was fortunate to do. I mean, this was not my original experiment. This was done by big shots, but I mean, I can narrate what exactly happened. So this is called Foucault's. This is actually pronounced as Foucault, not Foucault. Foucault's rotating mirror experiment. So here is the deal. Let us say you have a light source. I will describe it schematically, and if you have any questions, we can get into the details of the experiment. There is a light source here. This is all done in a lab, which I would say is something like 15 meters long, and like maybe 5-6 meters wide. you have a source of light. Actually, it's a laser beam, so that you have kind of pointed beam, and the light travels and let us say it hits a mirror. It hits a mirror and it comes back to other. It comes back like that. And let's say there is another mirror. So light will retrace its path, and it comes back to exactly where it started off. Right? You can create such an arrangement. Once you have created that arrangement, what you can do is you can take away this stationary mirror and you can replace it with a rotating mirror. Let us say this is a rotating mirror. It kind of rotates. It will take different orientations. And now what exactly is going on? So a light beam hits the mirror. It will be in some form or the other, right? And then it will, if things kind of nicely match, then see, if the mirror is something like that, it may just go there. I'm not interested in that at all. But in that continuous rotation, there will be a situation where the mirror will assume this position, in which case the light ray will come back. It will hit this mirror and go back. But by the time it returns back, the mirror will not be waiting. The mirror would have taken a slightly different position because it is rotating, which means the light will not retrace its path here. It will slightly get deviated.
So is it a uniform rotation?
Is
it a uniform rotation?
It's uniform rotation. It is uniform rotation. So do you see that there is actually a shift here? When light hit the mirror, it's a rotating mirror. It went somewhere and came back. But by the time it came back, the mirror was not waiting. It slightly rotated, which means the light will not further retrace its path. It will take a slightly deviated path. If you know how much the mirror has rotated, then can you tell me how much the light will bend, in the sense that there is this angle, right? There is this angle, right? That's an important angle now. If the mirror rotates by angle theta, by what angle the light ray rotates? Let us say this angle, which is the angle between the two positions of the mirror. Let us say that is theta. Can you tell me this angle theta here?
Sir, I think it is 2 theta.
It is 2 theta. Why is it 2 theta?
Sir, 1 second, sir. Like, I don't know how to put it in words, but like incident ray and reflected ray, no, sir. So in angle of incidence is equal to angle of reflection. So if you turn the mirror by theta,
you got it. So you would have learned this if the mirror rotates by angle theta, the reflected ray deviates by angle 2 theta. So and now the question is, how do you know theta? See, basically what is happening here? What exactly happening here is, see, this is an important arm. That's the real arm. This is not the important arm. Why is this an important arm? Let us call this as D. What is this 2D? 2D is the distance traveled by light in this journey. Within this journey, distance traveled is 2D. What is the time taken? The time taken you can calculate. See, if you know this deviation, some delta x, then you know some trigonometry, geometry and all, you can calculate this angle. 2 theta you can calculate. If you know 2 theta, then you can calculate theta. And if you know theta, and if you know how fast the mirror is rotating, let us say mirror is rotating at an angular speed omega. If you know this angle and angular speed, you know the time it takes for the mirror to rotate through this angle theta. So once you put that time here, you will get speed of light. That's the principle of the experiment. So now the question is, so this D is actually easy, right? Easy to measure. D is something that you can take a tape and you can measure it. The question is, can we really calculate this T? What are the things required to calculate that T? You need to know this angle.
So only the theta and the omega.
Correct. Theta and omega. theta is something that is geometrically related to this delta x. So you can actually measure delta x. You may require some maybe calipers or something. This is of order of like centimeter or few millimeters basically. So delta x is measurable. So if delta x is measurable and this arm is known, you can calculate theta, right? And the only thing that we are left with is this omega. And I'll tell you how we actually did this experiment. We took a mirror. It was actually a rectangular mirror. It was double-sided mirror as well. And then we took a drilling machine. We took away the needle and we inserted this mirror. And then we started operating it, which means the mirror is rotating very fast. And it actually requires a huge omega for you to observe a significant enough delta x. If you use some slowly rotating mirror, delta x will not be appreciable. Delta x, if it is something in nanometers, you have not achieved anything. So if delta x, yeah.
Sir, actually, sir, is the mirror, is it reflecting surface on both sides or only one side?
Both sides. You can make it even some hexagonal thing reflecting from 6 sides. It's better actually, because there are more instances of light actually retracing the first arm itself. Yeah. Go ahead.
Okay, so if we keep this plane mirror itself reflecting surface on both sides, then suppose it has oriented in that horizontal position where it light from the laser hits it and hits the second mirror, and by the time it comes back, it has rotated more than 90 degrees.
Okay, correct.
Then the light will from the second mirror will
absolutely yes.
First mirror will go that side. No, sir.
Perfect. So you are saying that there are two possibilities. That's what you are saying, right?
Sir.
So you start off from a slow speed and slowly increase the speed, right? In which case you will see the spot moving, spot actually moving slowly. See, if it is only one reading that you have, you always get the trouble. If it is a set of readings, then you can resolve the degeneracy, whether it's getting reflected off one phase or the other. For the current situation, let us say it was a single-sided mirror. So the double-sided mirror was basically to make sure that the intensity of light is large enough to observe, because there will be multiple lenses in between. Make sure that there is a parallel beam of light and all that. In every single transmission or reflection, there will be loss in the intensity. So by the time you get back the light, it will be really, really faint. You need a dark room and powerful enough laser to start with. Only then you can observe some mild light, because not all light will come back. So because the mirror is rotating, some of them will get thrown off in different directions. Only a particular section of light will actually come back. Okay, having told all this, how do you measure the frequency of rotation itself? That was somewhere around 1000 hertz or something like that.
Sir, we can have some in the cycle gear system, one big gear and one small gear, and we are rotating this, and then we know the gear ratio of both the gears, and then we have a sprocket. So when we are rotating the smaller gear and the bigger gear is turning. So we know the gear ratio, we know that.
That's a nice suggestion. That's a nice suggestion. Perhaps historically that would have happened. I'm not sure. But when we did this, we had a drilling machine, and what we did was the following. We after this experiment was done, for the same input of current which went into the drilling machine, we took, and then what we did was we shined a light, and then we allowed it to just get reflected on a LDR. Okay, what is LDR? See, resistance. It's actually a resistor whose resistance depends on the intensity of light falling on it. And then you connect the output of that circuit to a CRO. CRO is cathode ray oscilloscope. So now, whenever light falls on it, its resistance changes, which means the output fed to the CRO will have a nice waveform. If you measure the frequency of that time period of that waveform, you can get back the frequency of the light frequency at which light is falling rightly on that circuit, which traces back to the frequency of rotation of the.
Or we can know the RPM of the drilling machine, and then we can.
RPM will be provided by some manufacturer, right? Why should we believe that manufacturer? Knowing RPM is exactly same as knowing omega.
Yes, sir.
Yeah. But we kind of, why should we believe manufacturer? Maybe manufacturer said something wrong. As much as we get to scratch, it will be better, right?
Okay, sir.
Now, let me quickly ask you a couple of questions. One is that how do you actually understand this? So let us go back to the table. How do you theoretically understand this? How do you understand this? Okay, there is not much to understand here. You when you are traveling in a bus, okay, so it's not something very physical in that sense. There is no fundamental thing about bus moving. Okay, how about sound? What characteristics of a medium determines speed of sound?
So the density of sound.
There is a constant for the medium.
And
right?
what
for a given medium, there's a constant.
Fine. So so in one medium it is something, and in another medium it's something else, right? So
yeah,
what determines what characteristics of the medium determines the speed of sound?
Sir, I'm not sure, but is it solid, liquid, gas?
So in all solids it's the same speed, is it?
Sir, no, not like that, sir.
Nope.
All
sir, I would say the
okay. Somebody told
the
density.
chemical structure of the molecules.
See, but propagation of light sound is kind of macroscopic phenomenon. You can of course get involved with microscopics, and you can in principle always get an answer. But what are the bulk parameters that determine the speed of sound?
So can it be temperature?
Yeah, temperature and density. So the point is, if you know, for example, see, there are multiple ways to express it. You must have heard something called bulk modulus in elasticity. If you apply pressure to a medium, by how much will the volume change? That is given by something called bulk modulus. How easy or how difficult is it to compress or expand a medium, right? That is something called bulk modulus and density. These basically determine speed of sound. That's one way to put it. I mean, let's not focus on that. Let us come to speed of light. So you must have studied some electrostatics, right? Can somebody recall Coulomb's law? Force between two charged particles equal to?
Yes. Coulomb's constant.
K Q1 Q2 by R square.
What is K?
Sir, it's
the constant electrostatic.
It's 1/4 pi into E naught.
Epsilon
E
naught
naught being the medium.
E naught being what?
The medium.
What medium?
So not medium. Sorry, I forgot.
So there is this epsilon naught that gets into Coulomb's law, right? Do you recall its value, or recall the value of K rather? 1/4 pi epsilon naught.
So in vacuum, it's 9 into 10 to the power 9.
9 into 10 power 9, and then what? Kgs is it, or meters, or what? In some unit, in SI unit, it is 9 into 10 power 9, right? It's important that you remember these with units. Doesn't matter. Have you also heard something called mu naught? Where have you heard mu naught? Have you seen Biot-Savart law or something like that? Magnetism, that's correct. Magnetism, Biot-Savart law. Do you recall the value of mu naught? It's actually 4 pi into 10 power minus 7. Again in SI units. So now let us see what this quantity is. 1/root of epsilon naught mu naught. I can rewrite this 1/root of 4 pi epsilon naught into mu naught by 4 pi. And what is 4 pi epsilon naught? 4 pi epsilon naught is 1 over 9 into 10 power 9. And what is mu naught? Mu naught is 4 pi into 10 power minus 7. So what is mu naught by 4 pi? It is 10 power minus 7. And can you quickly evaluate this?
So square root of 1 by 9 into 10 to the power of 16.
Which is what? Square root of 9, you know, right?
3 by 10 power minus
1/3.
9.
3 into?
Minus 8. 3 by 10 to the power
minus 8 to the power of minus 8.
3 into 10 to the power of 8. The power of 8. 3 into 10 to the power of 8.
Have you seen this number before?
Speed of light.
Speed of light.
And if you put back units, it turns out to be meter per second. And this is not actually some kind of, I mean, this is actually a super exciting, right? You are dealing with some charged particles. You got familiar with this epsilon naught. You are dealing with some magnets. You got familiar with this mu naught. And you played around with this and you got speed of light. What do charges and magnets have to do with light?
Sir, could I just ask you something? I got lost in the last part of that.
No, I just did the calculation. I just did the calculation of 1 by root of epsilon naught mu naught. And we found that it is actually the speed of light. It is not exactly just this approximately speed of light.
No, I didn't understand part of the experiment.
There is no experiment that I'm suggesting here. So the question is the following. The question is, how do we understand? So what Maxwell was doing was he was playing with electricity and magnetism. He was formulating electricity and magnetism. Which one you're talking about?
So the mirror experiment.
Mirror experiment. We'll get back to mirror experiment. I'll complete this story and we'll get back to mirror experiment. Okay. So what we did here is, what Maxwell did was he was playing with electricity and magnetism. He was trying to formulate the laws of electromagnetism. Electromagnetism was already connected by Faraday's law. Laws of electricity and laws of magnetism were not independent by the time of Maxwell. But then he was playing out with this further, and he found that the basic laws of electromagnetism, which in today's language we call Maxwell's equations. You will see it in a typical BSc or MSc course on electricity and magnetism, what are called Maxwell's equations. They can be kind of rewired, and you will get what is called a wave equation. What is a wave equation? For example, if you have a Veena string, and then if you plug the string, you will get some shape and all, right? Now the question is how fast that shape moves. That determines that is actually determined by some characteristics of that string. What is the tension? What is the density? And all that stuff, right? Similarly, what is the kind of underlying equation obeyed by this wave? He was actually playing out with the laws of electricity and magnetism, and then after some kabaddi, he found that it can be beaten up to a wave equation. And whatever stands in the place of speed of that wave was 1 by root of epsilon naught mu naught. And that turned out to be speed of light. So
he found out that electromagnetic waves move with the speed of light.
Correct. Which actually led him to say that, look, light is basically an electromagnetic wave. And then that's not the only thing. Then you can very quickly, once you get into Maxwell's equations, you can very quickly see that why light has to be a transverse wave. You would have heard something about that, no? Polarization and all that. Why is light a transverse wave? Some picture and all you would have seen. Electric field and magnetic field. Some picture. All that picture comes out of electromagnetism. So if you understand electromagnetism deep enough, then optics is basically a byproduct. Optics is not independent. This is something called unification in physics, which is a very, which is actually a fun.
Yes, sir. And how does this relate to Aurora Borealis?
I'm not sure why
because
you mentioned.
No, because sir, we know that this can explain this whole relation between light, electromagnetic radiation. This is related to auroras, right?
No, not exactly. So you have a charged particles which actually respond to the magnetic field of Earth. That's a regular kind of Lorentz law that gets acted on the charged particles, and they will kind of go on. They have a trajectory. You can track the trajectory, and it will get settled somewhere.
Yeah.
But I'm talking about something slightly deeper.
Okay.
Okay. See, the last part was basically an advertisement. Okay, it was. I'm not expecting you to understand in great depth what exactly are Maxwell's equations. It's an involved thing. You take a full course on electricity and magnetism in a BSc or MSc thing, and then you will understand what exactly they mean. But this is just some stuff. So I will leave you with a question. Do you know something that travels faster than light?
Sir, they say that
the electric
particles called as tachyons.
Sir, but it's hypothetical.
Tachyons are hypothetical particles.
Okay. Can you suggest something that I can understand that travel faster than light?
Sir, can I explain something? Sir, information.
Expansion of the universe.
Yes, sir. Information at the quantum scale, information can move faster than light.
What about some macro scale?
The universe.
Macro scale, we haven't proven anything.
Sir, I didn't understand what is moving information at the quantum scale.
I also didn't understand. So I wanted.
Sir, can I explain?
Hey, by the way, laser is actually light, and laser travels at speed of light.
Yeah. Sir,
the question
can I
is, what
explain
travels
what I meant?
faster than light?
So this is a bit complicated, but
no. Let's not get into quantum mechanics at all. Whether it exists or not exists is not the point that I'm making. The point I'm making is, so what you're I understand what you're saying. You are relating something to what is called EPR paradox. Okay, so that's not what I'm asking. In some sense, fine. So let me ask you a question. Can you imagine a situation where shadow travels faster than light?
Sir, they both are equally. They both are parallel, sir. The speed of light.
Shadow travels faster than light.
A very, very long way to go.
Sir, can you explain what do you mean by shadow travels faster than light?
I'm asking you, imagine a situation where shadow travels faster than light.
So, assuming you have
Assuming you have what?
Yes, sir. I can think of a situation.
Yeah.
So, like, you have a very powerful torch, for example, shining on the moon, and you have your finger in front of that torch casting a shadow. If you quickly move your finger in front of that torch, you can have the shadow moving faster than light on that moon because it's updating so quickly.
Where is the shadow falling? Falling on a screen which is very far away, right?
Yes.
Yeah, that's actually right. What he said is actually right. So if you have a source, and let us say you hold your finger here, and then some shadow falls, and let us say that that screen is some light years away. Okay, so now if you move your finger, then
the shadow will be not only will it travel faster, but it will be like square kilometers huge.
You can make this arbitrarily large by making this distance arbitrarily large. If you make the distance between the setup and the screen larger and larger, then if you move your finger, the speed at which the shadow moves will be larger.
Also, if you sufficiently reduce the diameter of the torch, then also your finger
not
becomes.
I assume it's a point source and it is emitting light in all directions, and I move my hand. Now the shadow actually travels faster than light. The question is it violating some fundamental law of physics? It's not violating some fundamental law of physics, but
it's not.
That is something that has to do with some amount of relativity, which will not get involved now. Okay, so the bottom line is speed of light is interesting. That's the message I wanted to convey. And there are lots of things around speed of light. We have seen some aspects of speed of light. There is still a whole bunch of stuff. As I told, the second half of 19th century and the early part of 20th century was, you can just describe it as some journey around speed of light, some journey around light, particularly with relativity. Light has a very important role to play.
Sir, I've got a doubt. It's a hypothetical question. Like, I don't think you can do it. So let's say you're looking at a clock, and then the lights hit the clock, and then it hits your eyes. So if you move back looking at the clock at the speed of light, so the clock will show you the same time, right?
So see whether light hits it or not. Okay, let me rephrase your question. So what you're trying to say is this time dilation in relativity is because light is taking some time to travel and come back. Is that what you're saying?
Yeah, exactly.
Actually, it so happens that time dilation or length contraction that you typically study in special relativity has nothing to do with this extra time that light takes to go and come back, and some information is
it's something completely different.
It is completely unrelated to that. You account for all the time that light takes to hit something and come back and all that. On top of that, there is extra time. That's time dilation. So light need not get reflected from a clock and all that. You do such experiments to basically make sure there is something to hold on, because the postulate of relativity is that speed of light is universal constant. It's same for everyone, and you can hold on to that fact to make some computations. That's the point. But the time light takes for reflection and all that is immaterial.
Sir, one question.
Yeah, go ahead.
Faraday showed the relation between electromagnetic and light. Can we show a relation between these two and gravity also?
With what and gravity?
Electromagnetics, light, and gravity. Can we show a relation between these three?
If you do it, you will be very famous.
There hasn't been anything done so far.
Gravity is not yet into the game. If you pull gravity into the game, as I told you, will be very famous.
Sure, but isn't that what Einstein did? Because Einstein showed a relation between light and gravity with relativity.
No. Einstein studied gravity, and light also plays important role in GTR, special relativity, and general theory of relativity. But the point is the unification that I talked about, where electricity and magnetism were looked upon as two different things, and Faraday unified them. And then Maxwell unified optics also into that, and you can put in like the electromagnetism now can also take in strong forces and weak nuclear forces. But the point is this kind of unification, like looking at different phenomena as different phases of the same coin, does not still include gravity. Gravity itself has a very nice theory, which is general theory of relativity. But it is not into the league of electromagnetism and the other two forces, strong and weak nuclear forces.
Okay.
Are there any other questions? By the way, I just wanted to inform that, see, we have an undergraduate course in our university, which is Azim Premji University, and many of your seniors have joined there. And so the last day to apply is maybe 3 days from now. So you can Google Azim Premji University and you can get.
Sir, can you please repeat what you just said?
So we have an undergraduate course. There is also physics major that is offered, and there are many other majors. Bio major. There is humanity. Within humanities, there is English, philosophy, history, and economics is a separate major. And mathematics, we have biology and physics. These are the programs that we have. So physics program is certainly there. And physics BSc we have, and physics BSc B.Ed integrated we have, which is a 4-year program. So all these are nicely explained in the website. So if you go to Azim Premji University website, you can see more details on it. That's what I can quickly convey. It was really nice having this class. It was super interactive, and I'm very happy about that. See you all then. Bye bye.
Okay. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.